Test, test. Nice. All right, I think we'll go ahead and get started. Come up here. All right, welcome everybody. Thank you for coming to Pyowa. Welcome to Source Allies. My name is Matt. I organize this group. Couple things real quick. We've got pizza and drinks over there. There's additional drinks through the back door right here. Restrooms are up the stairs through those doors. Wi-Fi password is right there. Help yourself to any of those things. Let's see, what else? If you're interested in speaking, sponsoring, or hosting future Pyowa events, hit me up. Also join our Discord. We have an organizers channel in Discord if you're interested in being involved in any way. Everybody's welcome. I think that's all I've got. With that, I will hand it over to our speaker.
Okay. Okay, thanks. Happy to be here. Adam Best, work at Tractor Zoom as a senior data engineer. So let's jump right into it. A little about me. Got 6 years of data experience as a data engineer. Used to work at Deere, General Dynamics, IT, doing a lot of Oracle PL SQL. So that's where I first got started with bigger data sets. Had some experience at Pyowa with doing data platform and AWS data warehouse work there. Worked at John Deere Financial for a little bit, doing basically database admin and DevOps on AWS. And then currently at Tractor Zoom for about two years, doing data platform, AWS, Databricks, and a whole bunch of other stuff. But overall here, just wanted to cover what I want to cover here is just kind of giving an understanding of when and how DataFrames should be used, when they should be used. Go over some of the options for what libraries are out there. See what options you should or might want to use, and then a deeper dive into Daft as an example. What we cut it off a little bit, but what we're not going to talk about is like the exact syntax. The docs are on the websites. I don't need to read those to you. I'm not going to cover like how to build a data pipeline out of the scope, and then it's the hot topic, but I'm not going to talk machine learning, AI, agents, any of that. So covering kind of what I'm going to talk about is like I feel like data frames are a way to stir the data, mix it up, do some manipulation, trying to figure out what you want to do with the data, and that's just kind of a fun comic about that. So before I get too into it, how many of you have heard of DataFrames? Oh, hopefully everybody. How many have used a DataFrame library? Yeah, most. Okay. And then how many of you guys have used it in production rather than just kind of experimenting? Yep. Okay. Cool. All right. At a high level, just a data frame is basically a table, tabular data structure, rows and columns. For the most part, each column has a consistent data type, so we don't have mixing data types within a column. Columns are generally aligned and indexed, and the key part I want to cover is the operations on a data frame are typically like what they call vectorized, where you can do an operation on a column and it will do that operation simultaneously on every row in that column. It's what I think is probably the main benefit of a data frame. And then just it provides more built-in methods for doing data manipulation to make it a little bit easier. So some common tasks: selecting, filtering data, doing aggregations, sums, counts, group bys, and then joining or merging data sets. So you have two different data sets, want to merge, combine them in some way. We've got ways to do that. So a couple ways to create a data frame. You can do it from a list of dictionaries, dictionary of lists, NumPy arrays. That's for the most part just pandas. Read it in from files. A couple of options are CSV, JSON, Parquet, Excel, and then SQL, and you can also read from a SQL database. So run a select on your table, create a data frame. Some kind of the essential tools, I think, for checking out what's in your data. Checking the first and last rows. The info. I should preface this by saying these are pandas specific commands. For the most part, every library has something similar. It might be called something a little bit different, but these are everything is going to have at least these, I think. So yeah, checking first and last rows, generating a summary of the data frame, doing a statistical summary of numerics, getting rows and columns, number, and then some more descriptions on the columns themselves. So just a quick example of pandas: filter or select column selection, row selection, and something with pandas in particular, the row selection by integer. Not all libraries support that. And then Boolean indexing, so checking if a value of a column is within a range or greater than. Some other examples of typical things to do: checking for missing values, replacing values, and removing values that are missing. And some other ways to do some data manipulation. You can add new columns from existing columns. You can modify existing columns to change the data within. Can remove columns, rename columns. Pretty much most things that you can do in Excel. But the key feature here is all of these operations are vectorized. So every operation you do, all the rows are manipulated simultaneously. It's very, very efficient. Just sorting, grouping, aggregating, examples of those. And then combining data frames. So merging, joining, the same concept there, and then a concatenation, so that's more like a SQL union, I would say. So we're joining the two rows into one data frame. And for an example, just a simple data frame, Name, age, city are the columns, and the values are in arrays there. And then the output on the bottom. Oh, I might have to, okay, there we go. Yeah, and then we got the output on the bottom of, that's what that table looks like. So what isn't a data frame? We got like an example would be a list of dictionaries, list of of list. The key differences here are with these types of datas, you don't have the key feature lacking is that we don't have that operation ability to operate on all records at the same time. The dictionary of list is fairly similar to how data frames are normally conceptualized, where we have a column and then a list of values, where there's not really a relationship between individual rows. And then one more example is going to be named tuples or data classes, where we have a list of a class and we're creating that list. The other issue there is, we don't have the operations of doing all the things to a column at the same time. So if you wanted to multiply the age by 2, you have to kind of go through each record individually and multiply that value. Another example of not a data frame, SQL tables. It's very similar in concept because usually databases have that optimization built in. The lacking feature here is what you get from Python or another functional or object-oriented language where you can take pieces of code and reuse them so that it's more reusable. You can test it. It's pretty hard to do that with SQL. And then just a fun comic on the vectorization. And then I'm going to show you an example of like how wickedly fast it can be. So this would be just an example of where we have a large data set. It's 1 million rows of synthetic data. And then I'm just doing a silly operation of what's the ratio of the zip code to the ID in this data. So just checking like how fast is this? I'll go to the next example. This would be the non-vectorized version. Again, this is just pandas, but the thing to know here is the apply function. That's saying do the function above one row at a time. So run this function every row. I ran it. It's not super slow, but how fast is it in comparison? Really fast. Again, that's 1 million rows. And the optimization there, it's always going to depend on what you're doing exactly. It could be much slower, or probably won't be slower, but how fast it will depend. And then like each of these examples of non-data frames, it's some sort of structured or semi-structured data, but only the data frames add that vectorization piece to really speed up your data. So like what I think of when to use a data frame. when you're working with hundreds, thousands, records, columns, when you know performance is really important, or if you know the data itself is going to scale or needs to scale. The other thing is you need to make sure you have the space for the dependencies. A lot of these libraries are not very lightweight. I have, for this code here that I'm running, I was just curious. I was like, how many dependencies do I have here? And I had 117, but that's installing multiple of these DataFrame libraries. Some of them shared dependencies, but it's generally not a lightweight tool. So then, yeah, when to not use DataFrame. If you're not working with a lot of data, or if not expecting it to grow, or as I like to say, like if you think, Excel is fine, I can do this with Excel, that's fine. You don't have to use this. All right, so if you want to use a DataFrame, what are the options that are out there? And I'm going to go over a few these 5 options. Covered a little bit of pandas already, but the other is PySpark, Dask, Polars, and Daft. Going over just like a summary of pandas here. Pandas has a very large user base. It's been around for a long time. It's very mature. It has a lot of issues though. It's very much like, I believe it's almost entirely single-threaded. It's very memory, you're constrained by memory. So if you have a data set that is larger than memory, it's not gonna work. And then it's, on the back end, it's running C-ish, C Python. But it also integrates very nicely with, if you're using NumPy, Matplotlib, Seaborn, some other machine learning type libraries. Works very nicely with those. And just an example. Yeah, just an example. Here we got a pandas data frame, doing a little group by in there. Nothing too fancy. Next one I'm going to talk about PySpark. It came out as open source in around 2010. So it's a little bit older than pandas, but it is very, very scalable. So the original use case was like I don't recall the exact company, but it was like they had tons and tons of these tiny little PCs, and they wanted to scale their data sets against all of those compute nodes. And this is what it's built for, essentially, is hugely scalable to multiple nodes of individual compute. And then it's also very fault tolerant. So if one of those PCs decides to drop out, give up, it'll recover itself from that. And then the back end there is it's using JVM or Scala in the back end. But the downsides here is it's got a very high overhead if you have small data sets. So if you're working with like under 1 million rows, it's not really that necessary to use. And then it's also historically fairly difficult to host and run Spark by itself. It's gotten easier over time, but still not the easiest thing to work with. I'll say especially for debugging. And yeah, compared to the pandas example, it's a lot more verbose. have to bring in a lot more stuff to just define a data frame. But at the end, yeah, we got a plain old table at the end there. Next one to talk about, just quick overview, Dask. Came out open source in about 2015. Can do a parallel or lazy evaluation. So part of what Spark is built to do is do processing lazily, so only as it needs to. So if you say, if you create a data frame, realistically it's not actually going to do anything until you tell it, hey, I want to print the first row of that data frame. Dask is similar to that, where it's only going to do it when it needs to. But it's also got the API itself that it uses is very similar to the pandas API. It's kind of built to address a lot of the issues that pandas has. So it's able to do larger than memory data sets based on Python, but running pandas behind the scenes. As it says, it delegates to other libraries to actually run these processes. So a quick example, very similar syntax compared to pandas, but yeah, pretty similar. Just note that, yeah, you need that some sort of, hey, I want you to actually do what I told you. All right, and then next one, Polars. It is, yeah, open sourced in 2021. It's very fast. It's built in Rust, and because it's a little bit newer, I think it's a little less flexible for kind of the edge cases or things that are outside the normal wheelhouse. But it is really fast. And then just another example, doing a group by on that same data set from earlier. Just a little bit syntax in this area. And next one is Daft. It's the newest one of the ones I'm talking about here. It's not actually out as 1.0 yet. But it is, yeah, Python, Rust, and SQL. So it's kind of a combination of all those. It is able to scale to multiple compute nodes, similar to Spark, using an open source distributed execution engine called Ray. And then it's backed by a company called Eventual Inc. And then the other, it has a lot of nicer features for if you're working with cloud-based storage. Some newer features with that. And then just a quick example of that. Same data again, same group by, just yeah, showing that it works. And then comparing each of those 5 side by side is kind of interesting. So these are all doing the exact same operation. It's taking a data frame, grouping by city, finding the average age in each city. I just want to note that like pandas and Dask are very similar. Part of that is because of that, they share that back end of Dask is basically running pandas behind the scenes. And then Polars and Daft are also very similar. So I want to dig into it. I didn't have a time to, but I think Daft does a lot of things shares a lot of code with Polars in the back end, because they're both Rust based. And then we got 5 different libraries. The only ones that are exact same are pandas and Dask. Wouldn't it be great if they all used the same library? So there's actually tools out there to do that. IBIS is one of them. Basically, they've created backends for, as I say, 20 different backends. So the front end you actually work with, it's all the same, but you can use any of those backends. And it's all the same code. So if you wanted to use a different backend, it's one line change. Another example, Modin. These are quotes from their docs here, but I wanted to mention, they're mentioning here koalas. Koalas is a API layer of pandas on top of Spark. It's now just called Pandas API on Spark, so they're a little outdated here, but again, it's just they're trying to make it easy to use any of these tools with the same code, essentially. And then another mention of from Modin. I thought it was interesting that it mentions like all the row parallel operations. So that's something that's kind of specific to pandas. Normally these libraries, they don't like you to actually identify rows individually. It's kind of an anti-pattern. They want you to use those vectorized operations so that you don't have to go through each individual rows. And then just a quick kind of a graphical comparison. Nothing as a review. Like pandas has a lot of issues, but it's very easy to get started with. Very easy to kind of get going off the ground. Polars you can do very fast. Can manipulate huge files. I'm not going to go through all that. But of these, I think my slight favorite, as I was going through this and learning each one of these a little bit more, is going to be Daft. And then I was doing some more research and found this another comparison table from Daft. And this kind of has another set of features. And as you can see, it's advertising Daft here, as they're the only ones that check all the boxes. But it's a handy comparison to keep an eye out. I'll mention the arrow backed, so that that's a column there. On the back end, it's saying they're using the Apache PyArrow. So that is, if you've heard of Parquet, it is a similar storage as Parquet, except it is in memory. So that's part of why Polars and Daft are able to do these things so quickly. And it's very, very efficient. And so I used a little in the code I have here. There's a benchmark that I built, just kind of a quick comparison of, hey, these are all doing the same exact thing, same exact data set, same exact output. So I was just curious, what's going to be the fastest, what's going to be the slowest? As you can see, so the blue is CPU time, and then the green is memory usage. I guess the not surprising bit, pandas used the most memory because how it has to use, it has to load that entire file into memory. Interesting thing next is Dask. Uses a lot less memory, but a lot more CPU. My guess is because it's doing a little bit more overhead of managing smaller data sets. That's why it takes a little bit longer with Dask. Then Daft and Polars, since they're similar backend with the Rust, fairly similar runtimes and low memory usage. And then I'll mention I don't think this PySpark one is accurate 100%. I think there's a bug with how this scaling tool works. But yeah, if anyone knows how to fix that, happy to. Because PySpark is running in a separate process, it's not actually able to analyze that, at least with this scaling. All right, now digging in a little bit deeper with Daft. I've got this taxi trip data set, and I'm just going to load it. It's a CSV, loading it into a DataFrame. And I'm just going to show a quick sample of that. So we got 700,000 rows. It's got a variety of columns here. Just threw out a question for this. Is like, well, let's see how many trips it had a distance longer than 10 miles, more than one passenger. This would be a typical way to do that. So we're creating a new field that is a Boolean of checking this and this. And then we are doing a group by on that and getting a count. And then outputting that last data frame to the console here. So as you can see, ran super fast. As I was looking at this, I was like, that's interesting. Why are there 8,000 nuns? So digging into that a little bit more, took those 3 columns and said, hey, show me the nulls there. So we got within that data set, there's probably 8,000 or so where the passenger count is none. And that's part of why kind of understanding how these libraries work under the hood helps a lot, because I was not really expecting that to output as none. And each of these libraries might do something like that a little bit different. But that, and a quick example, this is Polars again, or Daft, but can also handle nested objects. So if I have say I want to get all keys where a nested value is a specific value, it's easy to do that. Then just an example of lazy execution. So I just told it to do a filter, select certain columns, order by an amount, and then give me 5 rows. As you can see, it didn't actually process anything. It takes a little bit longer, but when you do the show, then it's actually going through and actually running that process. And then an example of joining some data sets. So we've got our taxi data from earlier. Got another data frame that is just two locations. And I'm saying I want to join on that location ID. And yeah, simple example, but that's how it works. And yeah, so some going into Daft a little bit deeper here. These are probably more specific to Daft. One of the features that they offer is like it's very built around cloud-based storage. So it's able to read from a S3 bucket with one line, and it does it very easily. And yeah, so the data set I'm going to look at here is 37 gigs as Parquet data files. And I'll go ahead and run that. Hopefully the Wi-Fi in here is fairly decent. But yeah, that's fairly quick. I just said, yeah, show me 5 records where passenger count greater than 4. And yeah, it did that in a few seconds. And that's another example where that lazy filtering, and it's doing some optimization behind the scenes to kind of optimize for that. So it has a built-in tool of the explain to kind of dig into exactly why or what it's doing behind the scenes there. In this example here, I've got 2 different where clause. So where column 1 greater than 10 and then column 2 equals New York. So unoptimized, we have 2 different filter steps here. If we scroll down to the actual physical plan, it's combining each of those into one step. And just another way to kind of speed things up. Then another example here. Different process here, but yeah, we're doing thing to note here. So if we read this left to right here, it's a where clause followed by group by, doing an average, and it actually is doing the group by aggregation first, which is a little bit odd sometimes. So because of how that data is stored logically, it is faster for Daft to do that group by aggregation before doing an actual filter. As you can see, it's running that as a in-memory source here. And then going back to that query where I was pulling from S3, let's see what that looks like. So unoptimized, we're filtering and saying, show me all the data in this S3 path. And because it is a wildcarded path, it's looking for any files that match that. So we scroll down the thing to look that I think is interesting here. If we look at the actual physical of what it's doing, it's only looking at 6 of these files and saying, that's good enough for what you want. It knows that from these statistics, there is going to be at least 5 rows that match this condition. So it doesn't need to read the entire data set. And then this would be, I think, a little bit deeper into it, but if you needed to, or say you had a incredibly huge data set and it's not as fast as you want it to be, you can use this partitioning. So you can say I have two data frames, both have user ID. I'm joining on user ID here. If I partition those by user ID, that ensures that similar user IDs are in the same, they're collated in the same data set. So it's a little bit faster. And these are all very small data sets, so it's basically instant. And then another feature that's part of built into Daft is you can write things to a delta table, and so that this is bringing in some kind of SQL database features where delta offers the ACID transactions, so you can do that atomicity, consistency, isolation, durability. You got scalable metadata, and you can do time travel. So it's adding a little bit more features on top of what is normally just a Parquet file. And then I show an example of that. So we're reading a CSV and then writing it as a delta table to this path. And then reading it from that delta table again and showing 5 rows. It's a nice feature that you're able to do that with just one line. I should note that you do have to install the Delta Lake library as well as Daft. Oops. All right, and now, so going back to that ACID transactions bit, now if I try to write a different data set to that same location as a Delta file, I get a very angry message that says, hey, this table already exists and the data does not match. So it will prevent you from rewriting your data if you're not don't want it to. All right, and then just kind of wrapping up. As I mentioned, kind of every library is a little bit different. Each one kind of has a little bit of a trade-off. In general, they all make Python data analysis a little bit easier. Personally, I kind of like how Daft works. And yeah, I'm not affiliated with Daft or anything. I just think it's pretty cool. And some more resource links. Some of the research I did can find me on LinkedIn. I'm active on the Discord, and Tractor Zoom, my company, is hiring for my team. So if you know someone that might be interested, let me know. And some other links to the docs. All right. All right. Anybody got any questions? Yeah.
What resources would you run these different libraries on, like in cloud specifically? You
Mhm.
speak in general terms, and are there, from one library to another, would there be limitations where you couldn't run it on this type of resources versus another, that kind of thing?
Yeah. So the question was like, what kinds of resources would you run these libraries on in the cloud? And I guess one thing I'll mention is like I've done a lot with AWS Lambda, and there's a limitation in Lambda of your libraries and dependencies can only be so big. Some of these will not work in Lambda because of that. So that's why I mentioned that earlier, of being sure to make sure you're able to install all these dependencies. But in general, if you're doing just if your instance is just like a single node, there shouldn't be anything other than a pip install that's needed to run one of these. For the multi-node libraries, where like Spark or Daft using Ray, there's a little bit more involvement of doing that setup of connecting those nodes and different compute. Yeah, it can get pretty complex, but for the most part, any Linux, Windows, Mac, yeah, not too restrictive.
And for the complicated ones like Spark, there's like Databricks, there's hosted solutions too that you can
Right.
do for them to manage all that complexity. Spark has one, Dask kind of has one with Coil. Pullers has one as well, commercial offering.
Yep.
And I think you mentioned Dapt as
Yep.
well.
Yep. Exactly. Yeah. That's part of why. Yeah. Daft is it's sponsored by this eventual company, which is their product is basically hosting it for you. So yeah, it's all you can host it, self-host it, but yeah, it's a little bit more challenging. Any other questions?
I'll throw a really basic one. Earlier you added a column to show if it was just like a true physical in column.
Mm-hmm.
And then you did a calculation off that.
Let's see if I can find it.
Did you combine those two, or was that part of the vectorization thing? You needed to add that as a column first and then do the operation down?
I'll see if I probably won't be able to find that exact example, but for the most part, I shouldn't need to combine them, or I would be able to, you should be able to combine them, yes, in most cases.
Okay, so not a performance thing, just
Yeah.
decision.
Yep, readability probably.
If it's easy to pull up
Yeah.
the Dask benchmark, I'd be curious to see what.
Oh yeah. I can.
I used to work on Dask, so.
Oh, nice.
Oh no. If there are any questions, we should go to that.
And
If it's not hard, easy to get to then.
oh yeah, it's shit runs in 30 seconds here. I might have to change my window here. Let's see. And it's very possible could be something I'm doing wrong with the code, but it's also wasn't taking a whole lot of time with it either. How do I get this over here? switch my tab here. Yeah, so this would be the interactive one here. Yes, if I look into this,
So single CSV, is that right?
yeah,
Okay.
yeah, it's reading one CSV.
Do you know how big the CSV is by chance?
I believe it's the same 1 million rows synthetic people data.
Yeah, and then, okay. And that's basically the entirety of this group?
Yeah,
And
I,
there's, yeah, something around that.
um,
Okay.
oh yeah, and yeah, all the code is in the same library as this presentation. So
I'll check that out.
yeah, let me know what I'm doing wrong.
I would guess it scans the CSV first to find spots where it can split it. Because that's how DAS works. Partition.
Okay.
It needs to figure out where it can split it, and then
Hey,
maybe. But
gotcha.
I'll check.
Yeah. All right.
Is that where it avoids using the working memory? Is about partitioning it and then working with it? Or how, cause you remember you said that, like, I think the pandas has to load it all
Mhm.
implementations of your working memory, but the others don't necessarily do that. Is that what, are they piecing it out, or are they just like saving results? I mean, vectorized, they can't be line by line results, but
Yeah.
Yep, that's basically it.
yeah.
Chunks of pandas, DataFrames.
Mhm.
Knows how to combine.
Yeah. Yeah. See if I can pull up the actual repo here. Yeah, the link is in there. I can share the link to this as well, but yeah, all the code ran is in this repo. So, yeah. All right.
From an ML workflow, you mentioned pandas support. Do any of the other libraries have any integrations with like sklearn or TensorFlow or any of the major?
It would be, I know some of them do. Very dependent on the library. Yeah. Especially I know in Pandas 2, they now support PyArrow. So I would suspect there's a lot of overlap if you're able to use Pandas 2. All right, no other questions? Otherwise, happy to stay and chat if you want. I think that's all I got.
All right, everybody help yourself to more pizza, more drinks if you'd like. Stick around as long as you like and chat. Thanks for coming.